Now we're going to take a look at Simpson's rule, which will be our last approximation technique for this section. Simpson's rule is going to make use of parabolas to try to approximate areas under difficult curves. We'll start by kind of just highlighting here a couple important points. First, I'll state this. If I ever have three non-collinear points in the xy plane, that is, non-collinear points, meaning points that don't all form into a nice perfect straight line. Okay, so I can say that if I had any 3 points that don't form into a perfect straight line, obviously any 2 points form into a straight line, but as long as the third one's over on the side, I can call them non-collinear. They don't form a nice line. Well, if I have 3 points like this, then these 3 points uniquely determine a parabola. That's kind of a cool idea, that if you had any 3 points not in a straight line, there's actually only one parabola out there in the world that you could draw to connect those 3 points. It's kind of interesting. We're going to make use of that fact over here. We'll see that this is going to come into play on a curve something like this. So let's suppose that I took an x value right here, and I drew a point up onto this function. If I went over here, I could draw another point up onto this function. I could do the same thing at the very end. Now again, these points are not all in a straight line, and so there exists some parabola that can connect them. Let's suppose that that parabola looks something kind of like this, right? Seems like it would definitely have to be a parabola that opens up as opposed to opens down, and maybe it has something kind of like the following shape. Well, the interesting part then becomes our second bullet point. I can say that we see that the area under the red curve can be approximated by the area under the green parabola. Right? I can see that here on this interval, say, from A to B. Right? That the area under the green isn't identical to the area under the red, but it's kind of close. So this becomes kind of interesting. The nice thing with using these parabolas is that a parabola is a nice simple polynomial, and so I can definitely state that it's continuous. I can definitely state that then I'd be able to find an antiderivative and use fundamental theorem of calculus to find the area under the green, even if finding the area under the red is extremely difficult. Now, what happens if I try to start using multiple parabolas? Well, take a look down here. You can see that this portion of the red curve is somewhat similar to this portion over here at the right, where I have these kind of blue sections. But the rest of the curve is kind of new. And what I can see is that on each one of these different color coordinated pieces, I can imagine creating 3 individual points. And I can connect them with a parabola. That's kind of what I've done here. Notice that this is maybe only part of a parabola, and this parabola here might be like extremely wide, but just the portion that I'm working with is over there, and the area under it is highlighted in green. I have the same thing when I look at my next set of 3 points over here, and I can see a parabola type shape connecting them. Again, the parabola is not fully finished. I could kind of imagine this parabola moving off and maybe eventually coming down, but this is just a portion of that parabola. Again, since it almost looks like a straight line on this on this small section when I don't see the whole thing. Of course, my last portion over here, I can definitely see the parabola-like shape, right? Very, very easy to spot. And so what we can see down here is something very, very interesting. Again, every parabola requires 3 points, but it's the case that every 3 points make 2 intervals. Can't you see that down there? Those 3 points are going to create an interval and then another interval. Then I'm going to have 2 yellow intervals and 2 blue intervals. And so it's actually going to be the case that if n stands for the number of intervals used, not the number of parabolas, the number of intervals, then n must be even, because if I don't have an even number of intervals, I can't create parabolas. Every parabola requires 2 intervals, so I need to kind of create these parabolas by adding on 2 intervals at a time. So this becomes really important. When I'm doing Simpson's rule, n represents the number of intervals, and that number of intervals must be even. Now, we're not going to go through the derivation here of Simpson's rule, but you can see here what it looks like, and we'll talk a little bit about how to remember the pattern. You'll see that at the front I have something similar to what happened in the trapezoid rule. I have a delta x, but not over 2. This time it's over 3. I can then see that I kind of have this idea that my endpoint over here, this height on the very left edge and my height on the very right edge are going to be written down just one time, and everything in the middle is going to be kind of used multiple times over. Well, what we have seen here is that this pattern is actually going to occur where I'm going to say that I start with 4 of x1s, and then I alternate to 2, and then I alternate to 4, and then I alternate back to 2, and I just keep going and going and going until I finally get to my last item. What we'll see is that always the item that's right before the end and right after the beginning will always contain a 4. That's guaranteed every time. We'll see how to use this in just a moment. Also, though, with Simpson's rule, we see that we have a nice theorem that gives us an idea of the approximation error that might occur when using this method, much like we had for the midpoint and the trapezoid rules. A few key differences is that now I need a 4th derivative for my function to find k, and the formula over here is a little bit different in terms of the number on the bottom is a 180, much larger than before, and it has an n to the 4th, and on top I have a 5th power. So a quick thing we could note here is that the error bound has the potential here to be much, much smaller than the error bounds for the trapezoid and midpoint rules as n gets larger. Because as n gets really big, this is being raised to the 4th power, meaning this denominator is going to explode in size comparatively to what happens to trapezoid and midpoints. So for large values of n, Simpson's rule is going to provide us with excellent approximations very quickly. So let's take a look here at example number 4 and see how we can actually use Simpson's rule here in an example. So again, we're still going to be working with our curve of e to the negative x squared. So I'm going to go ahead and roughly sketch out again what that curve looks like. I'll mark on here the interval -1 to 1, roughly speaking. And then I'll say I want n to be a 4. Notice again that means or that follows the rule that n has to be even. But this means that this is a number of intervals, not a number of trapezoids. I can still calculate my delta x. How wide does each interval need to be? Well, my interval over here is still 2 units long, and I need to chop it up into 4 equal pieces. So that means I need to create things that are a half a unit long. Well, -1 to 0 is only 1 unit long. So to get a half, I'm going to have to put in like a -1/2 and a +1/2. Now I can see I have 1, 2, 3, 4 intervals over there. Okay, so let me go ahead and start to kind of create the parabola-like shapes. So I can see over here, I have 3 points, and I can imagine connecting them with a parabola. So let's see. This would look like maybe a parabola that opens downward. I don't know, maybe it's a parabola that looks something kind of like this. I could imagine it extending to the other side. And I'm going to try to find all of the area that's under that parabola. Notice, though, only up until I hit this -1. On the other side, I can again grab some points. This time I'm going to use green points. Again, I kind of have a parabola that maybe opens downward, something like this, and I can find the area under it up until positive 1. So again, this might not produce the exact area under the curve, but hopefully it gets us pretty close. Following Simpson's rule then, we can see that the integral from -1 to 1, e to the negative x squared, should be roughly equivalent to my delta x, which is a half, divided by 3. Then remember, I'm going to start with f of my first x, which is -1. I'm going to write up here again, remember that f of x here is just our e to the negative x squared. As I continue the pattern that we saw in the box above, I can see here that this is now going to be 4 of the next x down the line, where my next point was drawn. So this is f of negative a half. Then I'm going to swap to 2. That'd be for f of x, or for f of 0. Then I'm going to go back to 4, f of positive a half, and then I'm going to go to my last point, so this should just be a single f of 1. I can clean this up a little bit now. A half over 3 is a sixth. F of -1 is going to turn into just e to the -1. I'm going to have 4 e to the negative quarter. I'm going to have 2 e to the 0, 4 e to the negative quarter, and I'm going to end up with a e to the -1. If I was to simplify this down just a bit further, I would see here that I get a 1/6. I'm ultimately going to have 2e to the -1s. I'm going to have 8e to the negative quarter plus a 2. I could factor a 2 out and simplify this a bit further. So this would be a third e to the negative first, 4e to the negative 0.25, and plus a 1. Now if I used a calculator to approximate this, I will actually find that this is 1.4944, which if you look back when we talked about our error approximations, specifically in example number 3, or right before example number 3, you'll see that this is actually extremely close to what the calculator gave as the actual answer for this area. Here, the trapezoid rule is doing a great job of approximating. Now, I might want to figure out how far off this answer is. So let's see. Suppose that I now want to go ahead and determine that if I had n as a 4, how bad might this approximation have been? Well, I can use that error approximation formula. Let's suppose that my function again is e to the negative x squared. Let's suppose here that I already give you the value of k. So the fourth derivative of x absolute valued is always less than or equal to 12. Well then, I'm going to go ahead and try to use this formula that I have here, finding the error on the Simpson's rule approximation. Well, I'll start by writing down again what we know. Again, we know that a is -1, b is equal to +1, n up above was equal to 4, and we were told here that the value of k was equal to 12, right? That's what we had. So that means that the error in using Simpson's rule can either be equal to or smaller than the following value. It was k times b minus a to the 5th over 180 times n to the 4th. And if I plug in my different values, I'm going to get this. Now, if I was to go ahead and crunch all this out, and you can double check me on your own calculator, but I got down to a number that was like 384 on the top. I could get 46,080 in the denominator, or if you reduce it all the way down, it's 1 over 120, which actually is a nice repeating decimal, 0.0083, and the 3 is just repeating forever. But notice again what this tells me. This tells me that the error in this Simpson's rule approximation is either this much or less. So, thus, the approximation in part A has an error of 1 over 1/20th or less. Now, if I think about some of the implications of this, I can see in the decimal that if this is telling me how much error there is, then notice how much error is it telling me that there is in the 1 spot? Well, it's saying there's 0 error there, which means that I can trust completely that the actual area under this curve starts with a 1. It also says there's 0 error in the 10th digit, and that there is 0 error in the 100th digit, which means I can actually trust the first 2 decimal places. So I'll say this means we can be sure that the first 2 decimal places of our approximation are accurate. That's incredible. And in fact, you can see that that's actually perfectly in line again with what we saw earlier in this section, where we found that the calculator approximated the actual area under this curve at about 1.494 with some other stuff afterwards. But we have something that's extremely close to that. And this is the value of doing these sorts of approximations. Now, to end this video, I'll quickly state that since we never went through and derived any of these error calculation formulas, it will never be required that you have those memorized for any particular exam. In fact, on exams, if you need those formulas, they will be given to you. However, it is up to you to understand how you will use them. Things though like the midpoint rule, the trapezoid rule, Simpson's rule, how to set that up, that will not be given to you, and it's assumed that you will learn how to do that so that you can answer those questions quickly and efficiently on assessments.